Thanks for the introduction. So this is joint work with David Basin and Eugen Salinescu. And as you might guess, it's on verifying systems at runtime. To give you in a nutshell what it is, so we have the system which is generating a trace, and the monitor is looking at this trace at runtime and checking whether a certain property, a given property, is satisfied or not. The monitor itself might give a feedback, might output or outputs a verdict, and that verdict is either escalated or fed back to the system, and for example might trigger the restarting of a component. More concretely in this tool, or I structure my talk in the following parts. I first give an overview of our system model we are tackling, then the traces we are looking at, then about the specification language we are using, and about how we do the monitoring itself. In a very simplistic setting, if the system is a state machine, then we can use the synchronous composition of the monitor, assuming that is given by an LTL formula. We can translate this to an automaton, and then we can synchronously compose the system with the monitor itself. However, this setting is often too simplistic because the monitor itself would block the system for actually continuing. So they always need to synchronize. And if you have a distributed system, this blocking of a monitor is not acceptable. And you have, in most systems, you have asynchronous communication, you have unreliable channels, and if you look at such a system, it becomes much, much harder what the monitor actually should look at and what kind of conclusion the monitor should conclude from what the monitor is observing. So the system setup that we are looking at is that the components are instrumented and send their performed actions or over a one-way channel to the monitor. The monitor receives these messages and processes them and outputs a verdict. However, we have very weak restriction on these one-way channels to the monitor. So there can be non-uniform message delays. So when the component sends a message informing the monitor, it might be received at any time by the monitor. There could be, and in the limit, this would be a message loss. So if a message is never received by the monitor. However, what we assume is that the components timestamp their messages to the monitor. Here, we make the assumption, which is a fairly strong assumption, that the timestamps are precise. The benefit that we get from this assumption is that the monitor can receive the messages in a linear order. So there are no clock drifts, no clock screws, and so on. And in practice, you can use time protocols that achieve a fairly good precision of the timestamps. So what is now the monitor observing? So in the limit, it's, since the action are timestamped, you can think in the limit it's a timed word. However, the monitor at each time only sees a finite prefix of this timed word. Moreover, since we have arbitrarily message delays, it can be the case that this timed word, this prefix has actually gaps in between. And these gaps might get filled when more messages arrive at the monitor from time to time. A bit more formal, so an observation is a finite word with the letters of the form where you have an interval that is describing either a time point in my timed word, or it's a partial function that is describing the action. And I don't give the formal definition here, the set of observations, but I only make the remark that the set of observations is inductively defined, and corresponds to some extent to the knowledge of the monitor of the trace at a certain time. So initially, the monitor doesn't know anything about the system behavior. And this is represented by this, by this observation. So the interval says there's a gap from 0 to infinity, and nothing is known what has happened in the state because it's a gap. And this observation can now be refined when a message arrives. So assume that a message arrives with a timestamp 1, where the predicate P is true. Then we will replace this letter by that word over here, where we have the left part, which is again a gap between 0 and 1. We have the time point where the predicate P is assigned to true. And then at the end, the prefix is again a gap from 1 to infinity. And then maybe the monitor might conclude that there will be no further action in 0 to 1. Then this time word gets refined by just dropping the gap, because the gap is closed by knowing that nothing has happened there. And then maybe another message arrives at the timestamp 5. Then we replace that interval by the 3 letters and so on. And this continues. And now we want to do reasoning about these observations that the monitor observes. And for this, we define a logic, a semantics for metric temporal logic based on observations and not on timed words. So the syntax is, as you might expect. I would want to highlight here, since we want to also do reasoning about data values in the trace, we have a freeze quantifier that takes a value from the time point and freezes it to a variable. I come to this in a second. Since we are dealing with gaps, the underlying logic is not anymore Boolean. We use strong cleaning logic, where we have true, false, and a third truth value for unknown. And we can partially order these truth values by knowledge. In particular, unknown is less than true and false, but false and true are incomparable because they carry the same amount of knowledge. Not truth, but knowledge. The semantics is more or less what you expect for the non-temporal operators. So first, to explain you the notation, so W is the observation, and we want to have the truth value at the position I in my observation, which is position in the word. And the new is the valuation for the variables, because we have the freeze quantifier. And in particular here, if we have the formula true, we know it's true. True is true everywhere. For a predicate, we first need to check whether the valuation is in the given interpretation of the predicate symbol, but we can only do this if it's actually defined. Otherwise, it's unknown. The Boolean connectives not and or are as expected. However, be careful, we are now using cleaning logic and not anymore classical Boolean logic. And the freeze quantifier is sort of a weak form of existential quantification. We pick the value from the register, which is stored in the state, and we freeze it to the variable x. That's all what's happening. For the temporal connective, just a recall. So if we are in the standard timed word setting, P until Q makes a statement that there exists a Q where Q is true. This must satisfy certain timing constraints given by the interval I, and continuously up to this time point P holds. If you want to extend this now to observations, we need to be a bit careful, because the anchor, so the Q, makes an existential statement of the existence of a time point. And the continuation P is a universal statement over time points. If we have gaps, we do not know whether there will be eventually time points or not in this gap. And this is, we have to adjust this, the standard definition a bit here. So the black part is more or less what you know from over timed words. The TP and the TC, they adjust, they downgrade more or less a truth value to unknown in certain cases where there's a gap. I refer here to the details of the paper. There's one artifact to state the properties of this logic nicely is that, I mean, true, I said earlier, true is defined to be true everywhere, even on a gap. And that might be a bit counterintuitive. And for this, we actually, on the top level, we define it like if it's a time point, we take the truth value from the of the evaluation function. Otherwise, we say it's unknown. And furthermore, we are not interested anymore in the concrete time point of the word. We're interested in the time stamp where it's true or not. And given that definition, then we can nicely say, have a nice property about the monotonicity. So, which is more or less saying, if you refine your observation, then you can only grow in knowledge in your truth value. So an unknown might become true or false, but a false or true will never be switched to unknown or vice versa. That will not happen. The word problem, I mean, checking whether an observation satisfies an MTL formula is p-space complete. That is not hard to say to see. Hardness is more or less a simple reduction from QPF. Membership, you more or less use the inductive definition of the semantics. Worthwhile here to note is that in a propositional setting, it's much simpler. You can do it in p time. So the complexity more or less comes from the data values. And you can see this also in the reduction. Now, what about monitoring? What are the requirements we have for such a monitor? The first, I mean, and these two are the correctness requirements. Soundness means whenever the monitor outputs a verdict, it needs aligned the semantics of MTL. And completeness intuitively means whenever it has a Boolean value, you also want that the monitor outputs this as a verdict. Here, it's worthwhile to note that such monitors that are observational, complete, and sound and complete exists. And that's more or less, you can easily see this by you're solving in each iteration the word problem, which is p-space complete. If you go to the classical setting, this is actually not true. You will not be able to have sound and complete monitors. The reason is that you only have the finite prefix of the timed word, and you need to reason about all possible extensions. And for MTL, the satisfiability problem is already undecidable in the propositional setting, so not even with the freeze quantifier. So how do we do now monitoring? This is the main loop. And I will sketch the steps and how the internal data structure is updated by the monitor. So first about what is the state about and how is it initialized. So the main data structure that the monitor is maintaining is a graph structure where each node corresponds to an interval which corresponds to an observation or to a position in my observation. Then we have a subformula, and we have a valuation. And here, initially, it's always the empty valuation because we haven't frozen any data values to it. Now, what happens if a message arrives? So the first thing is, assuming that the monitor receives a message with the timestamp 1, then it splits the nodes in which this time, with the interval in which this timestamp is contained into 3 parts, in the left part, in the middle part, and in the right part. We inherit then the nodes from the splitted interval. Then for the edges for the non-temporal connectives are fairly easy. They are more or less just copied from, inherit from the splitted nodes. For the temporal nodes, it's a bit more complicated because we have to adjust them. But more or less, this is what we get in this example here. Now, assuming also that we have a data value frozen at timestamp 1 to 3, so x is frozen to 3. This happens at this node here because it's the freeze quantifier. And then we propagate this data value down in our graph structure. So the empty valuation here gets updated where x is now assigned to 3. Here similarly, here we have to be a bit careful because we need to copy these 2 nodes, because this node might later on receive another data value from a splitted interval here. So this is why we need to copy the node and not just replace the valuation in the node. But this is what data propagation is about. Boolean values, it's somehow the opposite. You propagate the truth values or the Boolean values up, assuming that at the message that the monitor received, we had true for the proposition P, and the interpretation of the predicate symbol Q contained the element 3, then these 2 nodes evaluate to true. And we propagate now these truth values up. In the first case, it's very simple. We cannot further do the propagation here because it depends on the second argument of the implementation, whether this will turn out to be true or false. And here we do a similar thing. We propagate the truth value up. That becomes true. We can also delete the nodes. We propagate it up, and eventually this root node becomes true, and we output a verdict. I should be careful. I should note here there are a lot of side conditions because sometimes we have to delay the propagation because of gaps. So it's not as simple as shown here. So that more or less concludes my talk. So what I've presented is a novel monitoring approach, which is based on the 3-valued semantics for MTL. It accounts for data values, so this is an extension of MTL, and the whole monitoring approach accounts for message loss and message delays. And in fact, the correctness guarantees that we give also imply that the outputs of the monitor are prompt. So there's no buffering of a message received and then until enough message or enough time has elapsed, then the monitor outputs something. So as soon as the monitor can make a conclusion, it will output it. I should also say here that the soundness and correctness guarantees are with respect to the observations the monitor receives. So if you forward to the monitor wrong messages, it will output wrong results. In particular, if the timestamps are not accurate, it will output, or it will draw the wrong conclusions. It can only infer from what it gets. In the paper, there are also some experimental results on a prototype that we did in the programming language Go. So the results there are for data streams. We can process at the moment 200 or more events per second, depending on the specification. This is a performance that should be improved in the future, but for some applications already good enough. For the propositional setting, it's much faster. And this has to deal again with the data values. So the costly factor are at the moment how to deal with data values. And somehow it's not so surprising. On one side you have a p-space complete problem with data values. In the propositional setting you only have you are in p-time. The main dependencies of the throughput of our prototype is about the number of freeze quantifiers. More or less this deals how many different assignments you have in the data structure, the number of temporal connectives, and also the time windows that are attached to these temporal connectives, which is also not surprising. If the time window is bigger, you have to take more into account to make certain conclusions. And the degree of the out-of-order delivery may be a bit surprising. Sometimes it has a significant impact, sometimes it's almost nothing. So what is ongoing in future work? So as I already hinted at, so we want to improve our prototype and we want to improve the monitoring algorithm, and we want to undertake case studies, and in particular we are looking at the interactions of the components in a software-defined network and check whether they are satisfied during runtime in my network. Thanks.
So we have time for one question. While the next speaker sets up, I have one question. If the messages would come in order, would it simplify the problem substantially? Would it simplify the problem substantially, or it would be still in p-space complete?
Yes, it would substantially simplify the problem because so if the messages come in order, then this interval here will be there will be always a gap at the very end of my prefix. And it's very simple to split this one, because you split it, this interval doesn't show up at all, right? Because this is not a gap anymore. And you will always have this form, and actually you can completely ignore this one. So you only need the time points to take into account. So it's much simpler you do not have to take into account the nodes that you generate here and here.
Thank you.